All right, so today we're going to solve some log equations, and we're going to also check those solutions to see if they actually work in our log equation. That's called checking for extraneous solutions. So our overall process for solving log equations is to rewrite our log as an exponential equation and then solve it. Sometimes we need to rewrite our log equation as one big log using properties of logs. So we want a single log on one or both sides, and then we're going to rewrite each side as a single log and undo both. Sometimes that will work. All right, so if you want to take a pause, write this down, and then here we go. So right now, this is a log equation, and to solve it, we want to go exponential because you undo logs by going exponential. Exponentials and logarithms are inverse operations. So as I do this, this is my base, this is my power, and that equals that thing that we call the argument, but in this case 2x plus 1. Now if I just use my knowledge of powers, 5 cubed is 125, and that's going to equal 2x plus 1. From here, hopefully, everybody should be able to solve this. You're undoing what's being done to x in reverse order. So I subtract the 1, and then I divide the 2 to get my answer of 62. Now with log equations, it's always important to check that our answer will work. So if I come back up here, and really I'm checking to make sure that I won't be trying to log a negative, which we can't do. So if I try log base 5 of 62 times 2 is 124, and I can see that's log base 5 of 125, which is indeed 3. But I'm mostly concerned with the fact that that needs to be a positive number, and in this case it is, so that answer will work. All right, on to the next one. So again, I am going to try and solve this, but first I want to undo any outside transformations to my log. So if I had x, I would divide by 2, I would ln, and then I would subtract 6. Now that last do is the first undo. So I'm going to add the 6 to both sides, and I get 9 over there. Now, when I think of solving, my next step is to undo the log. And to undo logs, we go exponential. And remember, when you have ln, you have a hidden base of e. So I'm going to take my base of e to my power of 9, and that's going to equal the thing inside my log, which is x over 2. And now I check, am I done? Not yet, because I still have this x divided by 2. I really want x. So to undo dividing by 2, I'm going to multiply by 2, and I get 2e to the 9 equals x. And that is a very weird answer, but it is an answer nonetheless. So if I want, I could use my calculator and come up with a decimal approximation, but 2e to the 9th is an exact answer. The decimal would be about 16,206.168, which you could check. And again, if I think about putting that number in for x in my log, I'm not going to be logging a negative, so that should be all good. All right, next problem. Now I have 2 logs. So it's not about undoing any outside transformations. It's about I need 1 log. See, if I pull this over, I'm going to rewrite using the properties of logs to get a single log on one or both sides. So when I notice the plus in between, adding 2 logs is the same as 1 log with the 2 arguments multiplied together. So I've turned my 2 logs into 1 log. Now my next step is now I have to undo that log. I'm going to rewrite as an exponential equation and solve. So again, I look at my log and I say, where's my base? That's 3. Where's the power? Logs are our powers, so what it equals is the power. And that's going to equal x times 5, in other words, 5x. Again, if I do a little bit of arithmetic, 3 to the 4th, you should know is 81. And x is going to be 81 divided by 5, which I can leave as a fraction, or if you like decimals, you can do the division and know that it goes in there once and 6, and I believe that's going to be 16.2 is x. And again, I want to just quickly check if I put 16.2 in for x in my log, I will be logging a positive and all is good. Okay, we're going to just step it up just a little bit. So log base 4 of x plus 2 plus log base 4 of x is log base 4 of 35. So now I have logs on both sides. I'm still going to do my same first step as before. I'm going to rewrite using properties of logs to get a single log on one or both sides, which means combining these two logs into one log. And I'm going to get log base 4 of x plus 2 times x. And that equals log base 4 of 35. Now at this point, I could move it over and try and go exponential, but we're kind of at that place which is similar to our common base problem, right? When I had something like 5 to the 2x equals 5 to the 1, when my bases are the same, it only works if the powers are the same, and I create this simpler equation of 2x plus 1, which I can solve and say x is 1/2. We have something similar going on here. I have two sides of my equation, which both are log base 4. So this will only be true if this argument, the thing inside this log, is equal to the thing inside the other log. So I can simplify this equation by simply eliminating the logs and saying this, which when you distribute turns into x squared plus 2x, has to equal 35. Otherwise, my two sides will not be the same. Now we're getting at a quadratic equation. And so we have to think back to what we did last semester. How do you solve a quadratic? Generally, we try and set them equal to 0. So I subtract my 35 over. And then I always try factoring. Quadratic formula will work every time, but I'm a big fan of factoring. So I try and factor this, and I realize that if I have x plus 7 and x minus 5, that will give me my x squared, my positive 2x in the middle, my negative 35 at the end, and then I end up with the solutions of x is negative 7 or x equals 5. Now here's really, when we have quadratics, is when we have to worry the most about extraneous solutions. So I go back up to the very top, not to any of these middle steps, but I'm coming back up to the very top. If I put negative 7 right there, I am going to be trying to log negative 5. That is not possible because I cannot take 4 and put it to a base or to a power. I cannot take base 4, put it to a power, and get a negative answer out, which means that negative 7 is what we call an extraneous solution. So it solves this quadratic right here. It solves all these equations, but it does not solve my original equation. So I knock that out. Now if I put the 5 in, I will have a 5 plus 2 there. I can log 7. I can raise 4 to a power and get 7. And again, I can raise 4 to a power and get 7. And so, or 5, sorry, this would be a 5. So 5 is an acceptable answer, and in this case, it's my only acceptable answer. Okay, so we're going to try this one. Again, my first step, I have a bunch of logs, so I'm going to rewrite using property of logs to get a single log on one or both sides. I have this log and I have a subtraction and another subtraction. So hopefully you have mastered the log benchmark, and you can see that this overall equation, or this log, would become log of x. That's the only one with a plus on top in front, so that one's going on the top. This log with a subtract in front puts the x plus 1 on the bottom, and another subtract is going to put the 5 on the bottom. And then all of that still equals 0. So now I have one log on one side and a number on the other. My next step, so I can't just set the inside equal to 0 because that side doesn't have a log. So now I need to rewrite each side as and undo both logs. That one seems a little bit silly. Or I can, I'm going to just nix that. My next step is really just to go exponential in this case. So I think about what's my base, and again it just says log, which means there's a hidden base of 10, and that's going to equal x over, and I'm going to distribute to get 5x plus 5. And I'm going to turn 10 to the 0 into 1 because anything to the 0 power is 1. So now I have this equation. I'm going to change directions to x over 5x plus 5 equals 1. I have x's on the top. I have x's on the bottom. I want to solve for x. I want to get the thing I'm looking for out of the bottom. So if I multiply both sides by 5x plus 5, that will become 1 and leave me with x over here and 5x plus 5 over there. And now it's a fairly simple solving of subtracting my x and subtracting the 5. And x is, I'm going to divide the 4, so negative 5/4. Oh, I don't like the look of that negative. I'm going to go back and check. And sure enough, if I try and log negative 5/4, I can't do it. So that means that in this case, it turns out there is no solution. Okay, we're going to do a couple more. Remember, at any point, you could pause the video to think about what's happening. So we're going to look at this one right now. In fact, it might be a good time for you to try and do the first step yourself. When you look at this, what do you think you should do first? Well, I rewrite using properties of logs. I want a single log. I have 2 logs. Don't want 2 logs. I can't undo 2 separate logs. I can go exponential when I have 1 log. So this side right here becomes log base 6 of the adding in the middle tells me that I multiply my arguments. So I have turned 2 logs into 1 log using laws of logs or properties of logs. The next step, since I only have a log on one side, and there's nothing outside of that log, is to go exponential. Undoing logs with writing them as exponential equations. And I think, what is my base? That's 6. What is the power? That is what the log equals. And that's going to equal, and again, that thing inside, which I'm going to quickly distribute and get x squared minus 5x. Once again, I have a quadratic equation. And we solve quadratics by setting them equal to 0. First, I'm going to say that 6 squared is 36. I don't want the 36 over here, so I'm going to subtract that away. X squared minus 5x minus 36. And my next idea is to try to factor. So I'm looking for 2 numbers that would multiply to make negative 36 and add to negative 5. And I think about 9 and 4. So they are 5 apart. And since it's a negative 36, 1 is negative and 1 is positive. And if I need a negative in the middle, I want more negative numbers than positive numbers. So I'd want negative 9x and 4x. Okay. That will get me my thing. And now my answer, that disappeared, is x is 9 or x equals negative 4. And again, I have to check, though. I want to check, because this solves the quadratic, but does it solve my original equation? When I come back up here, I can put a 9 here and log base 6 9, because that's a positive. And 9 minus 5 is trying to raise 6 to a power and get 4. I can do that. But what I can't do is put in the other answer, that negative 4. If I try to log negative 4, I do not like that. I cannot do it. And so, again, that's what we call the extraneous solution. Okay, one last problem. I have 3 logs, all using base e. And so I can do a couple things. One thing I can do over here is use laws of logs to say ln of x cubed equals, and then I can combine these 2 into 1 log. Ln of subtracting is the 2 logs divided. And again, I'm left with not one like the last one where I have one log and I go exponential. I have logs on both sides with the same base. And this will only work if my insides or my arguments are the same. So this log equation becomes just an algebraic equation involving x and numbers. So how do we solve this? Well, the answer is very carefully. Again, I have x's on both sides. I don't want x's on both sides. So I would like to not have an x over on this side. So if I divide by x and divide this side by x, I'm doing the same thing to both sides. That's going to leave a 1 there. And I'm going to get x squared is 1 over 16. So I need to undo squaring. And I undo squaring by square rooting. So I'm going to get x is, and remember when we square root, we really should be doing plus or minus the square root of 1/16. And hopefully you recognize that I can square root the 1 and I can square root the 16 and I get plus or minus 1/4. But again, I have to think about, do these answers work in my original equation? And per usual, the negative is troublesome. So I cannot use the negative, and so actually my only answer is x is positive 1/4, because the negative is what we call the extraneous solution. Hopefully you are now ready to tackle your homework.